So here's what's going on today. We're going to do this lab activity. We're not going to do a lab report on it. I don't have the Chromebooks booked or anything like that. We're just going to do this activity for the sake of doing it because it'll be kind of a good review of the latent heat stuff we were working on yesterday. It'll also have a little bit of specific heat capacity stuff in it, and a little bit of review of kind of the idea of the law of conservation of energy as well. Okay. So what we're going to be doing is we're going to be going across the hall to the lab, and we're going to be trying to calculate or measure / calculate the latent heat of fusion for water. Right? Now, what's that number theoretically supposed to be? That's vaporization. 333 joules per gram. All right. So what we're going to do is we're going to try and see if we can get a number that's reasonably close to that. The way we're going to do that is we're going to take a known amount of water and we're going to add ice to it. And we're going to record the temperature change of the water. Right? So in doing this, what we're going to have, okay, is we're going to have an initial, we're going to have an initial temperature and a final temperature for the water. So we'll have a change in temperature for the initial starting water that we have. Okay, when we add the ice to it, we don't know how much ice is going to be in it. Okay, but we're going to add ice to it and we're going to watch the temperature drop. Now the temperature will drop until it gets to around what? 0. Right. Okay, and when it gets to around 0, it might not be exactly 0. You just kind of have to watch it. The temperature will stop changing. Agreed? Okay. Where is the energy from the water going when its temperature drops? Into the ice. Okay. So things we're going to measure. We're going to have the temperature change of the water. Okay, the ice isn't changing temperature, is it? Okay, we're going to have the initial volume. Okay, we're going to have the initial volume of water. We're going to have the temperature change of the water, and then when the temperature stops changing, okay, around, it'll probably be somewhere around like 3 degrees, somewhere between 0 and 3 degrees. Okay, when it stops changing, stops going down, then we got to take out all the ice that's still left in there. Right, so we're going to scoop out with our hands all the ice that's left in there, just put it in the sink. Okay, and will there be now more water? Yeah, there will be. Okay, because some of the ice will have melted. All right, so we're going to have a final volume of water as well. Okay. So knowing the initial volume of water, I'm also going to know the mass of the water that's changing temperature. So I'm going to know the mass of the water, I'm going to know its water, and I'm going to know its temperature change. What will that help me calculate? Right, how much energy it lost. Okay, and where did we say that energy went? To the ice. Okay, if I have the final volume of water and the initial volume of water, will I be able to figure out the mass of the ice that melted? Yeah, okay, because it'll be whatever the volume change is. All right, it's supposed to be mass of ice, not mice. Okay, mass of ice. All right, so I'll have the mass of the ice, and I'll also know how much energy the ice absorbed, because I will have calculated it using these numbers. That's the law of conservation of energy part of the lab. Okay, the energy lost by the water had to be gained by the ice in order to melt it. Right? If I have the mass of the ice and the energy used, will I be able to calculate LF? Yes, I will. Okay, so when we go across to the lab, these are the things you need to record. So maybe just take out a sheet of paper, okay, just so that we can take something across and record the data we need. We'll come back here and do the calculations once we have our data. Okay, so we're going to need an initial volume. Okay, we're going to need the temperature change. So you're going to have to record the starting temperature of the water and the final temperature of the water. Okay. Okay, and the final volume. Right? That's the stuff we have to record. Initial volume of water, final volume of water, initial and final temperature of the water. Right? Then we can calculate all the rest of the stuff that we need. We're going to do 2 trials. Here's how the trials will work. We're going to use a graduated cylinder, one of the big ones, the 100 ml ones, and we're going to put exactly 200 milliliters of water into a beaker. Okay, what's the mass of 200 milliliters of water? 200 grams. Okay, the density of water is 1 gram per cubic centimeter. Okay, so we'll have 200 grams of water. We're going to put the thermometer in there, and we're going to take the initial temperature of that water. Then we're going to add some ice. We'll just take a handful of ice. I've got a bag of ice there. We'll just take a handful, about like that, put it in the beaker, and then you'll start stirring with a stirring rod, not the thermometer. Okay, if you stir with the thermometer, it always ends up breaking the thermometer. They're not designed for that kind of torque. So there'll be glass stirring rods beside the thermometers. So hold the thermometer in there and stir with the stirring rod, okay, and watch the temperature. When the temperature stops changing, somewhere between 0 and 3 degrees probably, okay, when it stops changing, pull the thermometer out, the stirring rod out, and then have a group member reach in and grab as much of the ice as possible, give it a bit of a shake so no water is stuck in the ice, okay? It all gets back into the beaker, and then you can just dump that ice, all right? So then we'll have the final temperature. Now, once we have that water that's left, we need to pour it back into the graduated cylinder so that we can find out how much more water we have than we started with, because we have to record the final volume of water as well. Okay, everybody with me there? All right, we're going to do 2 trials, okay, just so we've got 2 sets of data to average out in case there's any error. All right, so that part won't take us, I think, too long, okay, and then we'll come back here. Now, when we're in the lab there, just again, remember kind of lab safety stuff. We don't need to wear safety goggles or anything like that. There's nothing harmful. We're just using ice and water. But I mean, if you're afraid you're going to poke out your eye with the thermometer, by all means, put a pair of safety glasses on. Okay. Or if you don't want to get wet, you can put one of the lab aprons on, whatever. Okay. Questions on what we're doing? Okay, let's head across the hall then. Okay, so watch and listen carefully here, guys. Okay. What we have to do here is we have to use the law of conservation of energy in order to know how much energy was needed to melt the ice. Okay, we know that the energy to melt the ice came from the water, so we first have to calculate how much energy did the water lose. Okay, so the first calculation we have to do is energy lost by the water. All right, if I'm going to do that, I'm going to be using E equals mc delta T because it lost kinetic thermal energy. Its temperature decreased. Okay, so here's what we're going to do. We're going to take the mass of the water, which was the volume was 200 milliliters, so the mass is 200 grams. Okay, so M is 200 grams. Okay, the specific heat capacity is 4.2 joules per gram degrees Celsius. And for the data that I have here, okay, it says that my temperature change was exactly 20 degrees. It went from 24 down to 4. Okay, so delta T is going to be 20 degrees Celsius. All right, so now I'm going to calculate how much energy was lost by the water. E equals mc delta T. All right, so we're going to have 200 times 4.2 times 20 degrees. Okay, so the water lost 16,800 joules worth of energy. Okay, so here's where the law of conservation of energy part comes in. If that was lost by the water, it was gained by the ice. Okay, so now the next part is I've got to know, I've got to use E equals MLF in order to calculate the latent heat diffusion for ice. Okay, I know this number here, E, is 16,800. I need to know how much ice melted. So for that, I go back up to my volume data. I started out with 200 milliliters of water, but I ended up with 265 milliliters of water, which means 65 grams of ice melted. All right, you guys follow my logic there? All right, so M is going to be 65. So to get LF, E divided by M, 16,800 divided by 65. Okay, and that'll give me my, well, what the latent heat diffusion for water for this data ends up being. Okay, and it's a bit off. And you know what, honestly, when we do this experiment, we rarely get close. Why? What are some major sources of error that we're not taking into account when we do this lab? Well, but we did take the initial temperature of the water. So we know what the temperature of the water was, whether it was room temperature or not. We could have started at 10 degrees if we wanted to. We just would have had a smaller temperature change. Okay, possibly, although most of the time we end up waiting too long. Like, we're waiting for the thermometer to stop and it's actually stopped, but we're like, did it stop? Is it still moving? So usually we go a little bit too long. We err on that side. Yeah, you're always going to lose a little bit of water when you're scooping out the ice cubes. That's certainly a source of error, but there's one huge source of error, and it has to do with energy. Yeah, you might create a little bit of friction when you're stirring it, probably not enough to make a huge difference, but it's there. Yeah, not so much that you lose energy to the surroundings, but you gain it. Yeah, we didn't take into account at all that this was happening in a room that was 23 degrees. Okay, a lot of energy that melted that ice wasn't just the water. A lot of it came from the surroundings. We didn't take that into account. Okay, realistically, the water did not absorb 16,800 joules worth of energy. Okay, some of that came from the surroundings. Some of it's added in there. Okay, so there's a pretty major source of error that's involved with just thermodynamics. Energy flows from hot to cold, and our surroundings were hotter than our experimental apparatus. Okay, does everyone kind of follow me there? Okay? And it's a pretty major reason why we don't usually get very close, and we're usually lower. Okay, very rarely do we do this experiment get a number like 400. Okay, most of the time we're quite a bit lower because the mass of water we get is too big. Okay, it's usually that less of that there should be less ice, that melted. Okay. How could we fix that? What's a way we could do this a little bit better? Okay, do it in a fridge, or we could use what's called a calorimeter. Okay, a bomb calorimeter, which is it's basically an insulated mug, essentially. Okay, that you can do this experiment in that reduces the amount of heat from the surroundings that would interfere with the experiment. Right. So we could say we could do that in the future. That would help to eliminate probably our biggest source of error in the entire experiment. Okay. All right. Questions on what we did there? That's not something I'm going to ask you to do on a test, but it's just kind of worth doing just to see kind of how that stuff works. All right, now we're going to move on to the next thing here. Okay, so I'll give you a couple minutes break while I'm getting the next thing ready, right? And then I think we might be able to gain one more day for final exam review if I can get through today and tomorrow. Get through this lesson today and tomorrow.